In this video, we're going to take a look at an introduction to a topic called improper integrals. And I think the best way to sort of introduce this concept is just with an example. Okay, so the first example we're going to look at, we're looking at integrating the function 1 over x squared. Okay, so I've drawn a sketch just to see what 1 over x squared looks like. It looks very similar to 1 over x in this part of the graph. The other part of the graph wouldn't be down there, it would be over this way as well, because it's symmetrical about the y-axis. But I'm only considering this section of the graph, because look at the two integrals that we're thinking about. Now, when you've got an improper integral, essentially there's sort of two scenarios. One of your limits can be infinity. And essentially, how we would describe that mathematically, we would say, well, the interval of integration is infinite. If you think about the diagram, what we're trying to do there is we're trying to find the area from 1 to infinity, which is all of this area underneath the graph. Now you might just say, well, if we're going all the way to infinity, sure, the area is going to be infinity, isn't it? But it doesn't actually work like that, because if you look at the graph, the function tends towards 0, doesn't it? So the answers are getting smaller and smaller. So this area might, although we're going all the way as far as we want as x tends to infinity, this area here might have a finite value that we can find. Okay? So that's one type of an improper integral. It's fairly obvious because you've got infinity as your limit. The other type of improper integral is a little bit more sneaky. So consider this one. If we were trying to integrate from 0 to 1, we're going to be finding the area between 0 and 1. Now, our function, 1 over x squared, it's undefined, isn't it, at x equals 0? Like, we've got a vertical asymptote for our graph. So if we did try and sub 0 into this, the y values would approach infinity, wouldn't it? So the interval isn't infinite, the interval's only this wide. But again, we've got this area which is tending towards this asymptote here. So you might think well, that area is infinite because it just goes up as far as you want to infinity. But we will see that we might be able to actually figure out a value for these areas. Sometimes it's undefined and it tends towards infinity. You've got an infinite area. Sometimes we can actually evaluate this area and figure out what it is. Okay. So for the first one, let's look at from infinity to 1 over x squared. And it's normally worth one mark this in the exam. It'll say, like, why is it an improper integral? For this one, you want to say that the interval of integration is infinite. And I would recommend that you highlight that in your notes, because it's like a common little 1 mark question that can be asked. And that's how it looks normally on the mark scheme. So don't just say, oh, one of the limits is infinity. Like, you need to sort of try and word it like this. We're thinking about this interval that we're integrating across. We're going from 1 to infinity, so this interval is infinite. Okay. Next thing, you don't actually want to sub infinity in, like you won't get the marks. So we're going to replace the limit with a letter. You can use whatever letter you want. I'm going to use the letter P. But you can literally use any letter that you want. So let's integrate. Index form. Add 1 to our power. Divide by our new power. Before we sub the limits in, let's tidy this up. So I'm going to write this as minus 1 over x between p and 1. Okay, so we would get minus 1 over p minus 1 over 1, which would be minus 1 over p plus 1. Okay. This is how you need to set it out. Okay, so don't start subbing infinity and you won't get the marks. Replace with a letter whichever limit there's a problem with, replace that one. And then say as p tends towards infinity, because we're thinking about the limit being infinity, but we've used a letter, and now we can use this limit in notation. So as p tends towards infinity, we can say minus 1 over p. Can we see what's going to happen? As p tends to infinity, minus 1 over p is going to tend towards 0, isn't it? Okay, so you've got to set it out like this. Please don't sub infinity in, like you just won't get the mark. So we can say therefore as p tends to infinity, minus 1 over p tends towards 0, so if that tends to 0, we're left with the integral from infinity to 1 of 1 over x squared. The actual area will just equal 1. So even though we tend towards infinity, as we get further and further this way, this area gets closer and closer to 1. Okay, so we know that area there is equal to 1. Essentially, because this tends towards 0 quickly, the area that gets trapped is never bigger than 1 unit squared. Okay. Now let's see if this one has a value, or if this one tends towards infinity. Okay, let's try this next one. Okay, so if we're going to say why this one is an improper integral, we're not going to say that the interval is infinite. The interval is not infinite, is it? This is our interval, we're integrating between 0 and 1. Instead, the problem lies with this limit and the function. So I would say 1 over x squared, like name the function, and then say it is undefined. At x equals 0. So that's the reason that this is an improper integral. So because there's a problem with this limit, we're going to need to replace it with a letter. Like don't sub in 0, you won't get the marks. So we're going to integrate from 1 to p x to minus 2. We've already integrated this, haven't we? So it's minus 1 over x. But now we're going to sub the limit 1 and p in. Okay, because we have to replace this one. So that would give us minus 1 over 1 minus 1 over p. So we've got minus 1 plus 1 over p. And now we're thinking about as p tends towards 0. But as p gets smaller, 1 divided by something that's getting smaller is actually going to tend towards infinity. So because this term is tending towards infinity, it doesn't matter about this minus 1, does it? Like if you've got minus 1 and then something which is tending towards infinity, that's basically negligible. Like, it has no impact at all on the answer. Like we can just completely forget about this. This term tends towards infinity, so therefore we have no finite value. So this area here actually just gets bigger and bigger and bigger the closer we get to 0. Like this area essentially tends to infinity. So we couldn't say this was, don't say it's equal to infinity, like just say that there's no finite value. Okay, let's try another one. So for the next one, we're integrating between 0 and infinity, and we're integrating x e to the minus 3x. Now, clearly we've got an improper integral because we've got infinity as our limit, but let's check 0. Like we can sub 0 into this, can't we? It's fine. The exponential function is defined for all values, like a negative exponential goes like this, doesn't it? So what we're trying to do now is think about the area between 0 and infinity. Just to give you an idea about what this looks like as well, I've drawn it on the calculator. So the function x e to the minus 3x looks like this, it's got this shape. And we're trying to evaluate the area between 0. Notice it goes through the origin at 0, so we're trying to find the area from 0 all the way up to infinity, like as far that way as we want. Clearly it's getting smaller and smaller and smaller, isn't it? Closer to this, the x-axis, which is like an asymptote. So is this area here, as far as we go that way, does it tend towards a limit, or does the area just get bigger and bigger and bigger? It looks to me on the calculator like this area gets really close to the axis very quickly, so I think we might be able to find out what this area is. But we're going to have to go through the process just to see. Okay, so we're going to say that the interval of integration is infinite. And we're going to have to integrate this using parts. So u would equal x, du by dx would equal 1, dv by dx would equal e to the minus 3x. So v would equal minus a third e to the minus 3x. So the parts formula, you do get it in the booklet if you can't remember it, but it's u times by v, so it would be minus a third x e to the minus 3x minus, inside the integral are the two new things, so v times by du, which would be minus a third times by 1. I'm going to take that outside, because plus 1/3 e to the minus 3x dx. So we've got minus a third x e to the minus 3x. Integrate this, divide by minus 3 again, so that becomes minus a ninth e to the minus 3x. And remember, we don't sub infinity, and we have to then evaluate it using a letter, whichever letter you want. Okay, so we've got minus 1/3 p e to the minus 3p minus 1/9 e to the minus 3p minus, open up a bracket. Okay, when we sub 0 into this, 0 would make that disappear. When you sub 0 into this, we get e to the power 0. Which is clearly 1, isn't it? Okay. So that will give us minus a third p e to the minus 3p minus a ninth e to the minus 3p plus 1/9. Okay, so now we've got to evaluate like what this limit that we've used, p, we're thinking about as p tends towards infinity. Okay, you will notice I've written this here. There's two special limits that we potentially need to use in this topic. It can come up in other parts of the course as well, but it quite commonly comes up on this part when we're doing improper integrals. Like, you need to know this limit as x tends to infinity. If you've got a polynomial, like an x to a power times by a negative exponential, that limit's going to equal 0. Okay, and if you think about it, like, we can't just, like, we've got to use it for this one. Okay, because if you've got minus a third p e to the minus 3p, you can't just look at that limit and evaluate it, because we're thinking about it as p gets bigger. So what we've got here is that term tends to infinity, like p tends to infinity, so that one's getting bigger, but a negative exponential gets smaller. So we've got a fight between a polynomial and an exponential. That's getting bigger, that's getting smaller, and the exponentials win. That one gets smaller quicker than that one gets bigger, so that's why the limit is equal to 0. But like, obviously we're going to say that tends towards 0, but we should, at this point, we should state, I'm not going to write it again because I've written it there, but to get the marks in the exam you should state this limit, and you can't just write that down. You need to justify that reason there. Okay, for the other one, it doesn't matter, that you've just got minus a ninth e to the minus 3p. So you can think, well, the negative exponential, like, don't forget the negative exponential graph. Just looks like that, doesn't it? So for that negative exponential, we know that as p tends to infinity, that negative exponential is clearly just going to tend towards 0. So that one that's not a special limit, but this one is. Okay, so that tends to 0, that tends to 0, and guess what we're left with? 1/9. So therefore, the integral of x e to the minus 3x is equal to 1/9. Okay. There's a couple more examples we can try where we've got different types of integrals, like with ln's and there's other types of limits. But I'm going to leave it there for now for this video. Nice one, guys.